from the Center of Research and Technology, ELAS, Dr. Nickolas Vlachos. Dr. Vlachos completed his studies in aeronautical engineering and doctoral work in computational aerodynamics at the University of Bristol. He joined the research team of the currently Artemis laboratory at CERN in 2001 and has been working on applications of multiphysics, multiscale simulations combining fluid flow, heat mass transfer, reactions, and particle transport in process systems and porous media. Dr. Vlachos, thank you.
Thank you, Kyriaki, for the introduction. Thank you to the NEUTRON project for the invitation for us to come and present today and to join your workshop. In a way, I don't feel like a stranger or a foreigner because of so many colleagues from CERN, of course, from other departments and teams with which we don't have a lot of contact. So what I want to show you today is to give you a brief overview of a project that has begun just 5 months ago. In many ways, it's maybe a step further from what Daniel showed very nicely in the previous presentation. Of course, nowhere near the level of maturity of the technology that was shown previously, the green heat module. It's called the Hercules project. It's the full title is High Temperature Thermochemical Heat Storage Powered by Renewables, such as photovoltaics and wind. And we are targeting industrial heating applications that require high temperatures. In other words, I mean, to put a number to that, in the range of 1,100 degrees or so for processes that need that. Okay. I'm sorry, the director of our team could not be, Dr. George Karagianakis, be here to present himself. He is responsible for our participation in this. So very quickly, some basic facts about the project. As I said, it was kicked off about 5 months ago. It has a 48-month duration due to end in May of 2027, with almost 4 million euro funding from the Horizon program, the innovation program, and specifically from the department of CINEA, the Climate, Infrastructure, and Environmental Executive Agency. It's coordinated by the University at Twente, and there are 10 partners from 6 EU countries. The partnership includes institutes such as ourselves and our colleagues at DLR, who are mainly at the thermochemical storage material development level and the chemistry and so on. There are partners who are ceramics manufacturers, therefore building components, building systems for the storage modules, integrators for such systems to include control and so on, and diagnostics. And there is an institute from Sweden that will be looking at the environmental impact and life cycle analysis of the technology as it's being developed. And we have 2 end users, Tata Steel from the steel industry, steel manufacturing, and Alucha also in the Netherlands, which is from an application in recycling calcium carbonate from the paper mill sludge. Okay, so this is very complete consortium. The origins, of course, as many will know, is from using structured bricks or stone or material that can withstand high temperatures to store sensible heat, as has been used in some industrial applications for recovering of heat from combustion flue gases. And this heated air stream can be coupled back into the industrial process, perhaps as preheated combustion air in some applications. Yes, so of course now with the availability of more affordable renewable electricity. We could say cheap, but it depends what you mean by that exactly. It makes sense to use renewable intermittent, let's say, sources of power, such as photovoltaics and wind turbines, to actually provide the heat to these storage modules, as was shown earlier for example, the green heat module, and other applications in other parts of the world with which the concept explored in Hercules shares certainly a lot of DNA and hopes to progress, to evolve into one level beyond. And so what do we expect to do? What do we think we can do in the Hercules project? I mean, it's not very easy to outcost rocks or high temperature bricks or slag, which is used as a heat storage, a storage material of sensible heat. We hope to be able to bring into this concept the idea of breathing bricks. In other words, heat storage material that can also store energy in a thermochemical reaction in a mixed metal oxide that performs a redox, let's say, cyclic reaction. So during charging, the bricks would exhale oxygen as they are reduced, and then they are ready for when we need this additional enthalpy to be discharged by providing oxygen, a stream containing oxygen, and the airstream which we want to heat to a higher temperature to drive whatever process needs it downstream. Okay, and this is something which we envision could be using air as the stream, let's say the fluid for driving this process, or perhaps in some cases, some applications, flue gases from the processes may be used in the system, depending, of course, on the durability or the interactions of the materials with the flue gases. So how do we justify the unavoidable extra cost and complexity for these breathing bricks, both in their manufacture and their synthesis and in their integration into the modules, the storage modules? Well, we see that this extra heat that you can generate during the oxidation or the discharging of the bricks can be exploited together with sensible heat, and it's possible to achieve without an additional, let's say, combustion source of energy, heat transfer fluid streams at temperatures which are higher than the incoming streams during charging. Okay, so this is, in a way, it's using the heat storage material and its redox capability as your fuel for your, instead of having a boosting, thermal boosting combustion module inside or section inside your system, you can use the additional enthalpy from this, the thermochemical storage material. Okay, and this is based, as I said before, showing it here a bit more clearly, charging the material in a reduction reaction, which may occur, typically occurs at a temperature lower than your application temperature, and then occurring higher than your application temperature, and then discharging the material by reducing the temperature and providing oxygen into the stream, the gas stream that is going to the thermal storage modules. Okay, and you can see a better overview of the concept here, the charging, and also its integration with the possible district heating network as one of the end users of typically the waste heat at the lower temperatures from this process. So when there is availability of surplus or sufficient renewable electricity. This is used, it can be used simultaneously to provide the process, the heat required by the process, the industrial end user. At the same time, surplus energy from these sources is used to charge the Hercules thermal battery, if we can call it that. And then during times when there is not availability of the renewable power, it is possible to supply air, for example, colder air as a stream to the thermal storage module, to the thermal battery, and extract the stored energy from the system, from the storage module. Typically, in the applications that we envision, we will have a shallower, let's say, depth of discharge, if we can borrow terminology from the battery sector, because the requirements for temperatures of the outflow stream for the industrial end user are typically more stringent than in situations where maybe you're producing power and you want to extract as much of the sensible heat as possible from your storage module. Okay, so there's some experience with other let's say, systems of redox systems for doing this kind of storage, which has built up to to the Hercules project. One example is the Restructure project, which was running in the years 2011 to 2016. This was studying the cobalt oxide cycle. Cobalt oxide is one of the materials which has perhaps one of the highest capabilities for thermochemically storing heat in a chemical reaction, such as a cyclic redox reaction between the two oxides you see here. This was pursued and from the level of basic material studies up to proving at the scale of a unit which had more than 80 kilograms of the cobalt oxide reactant in the system. And this was demonstrated that you could get very, very good and relatively reliable thermochemical storage, with some limitation, of course, in the cycle lifetime that could be proven up to the stage of this project. Very high thermal energy storage capacity in the thermochemical cycle of the cobalt oxide, but why are we not continuing this? What was the problem? Well, cobalt is a very critical material, and it also poses some potentially deleterious effects in the environment for human health. Furthermore, there is the high degree of change in oxidation state means that there are huge changes in the material structure at the crystal level, and it is very difficult to, or at least we were not able to stabilize the material structurally over many cycles, as you can see from some of these pictures, the pictorial examples here. Therefore, Hercules was a result of us looking at other mixed metal oxides which would do redox cycles capable of storing significant amounts of energy. Calcium manganate has been seen not only by us but also by others as a possible candidate, and this is one of the main candidates now in the Hercules project. It's able to perform completely reversible expansion and contraction as a structure from cycle to cycle, despite the fact that we have more than 2% change, elongation and contraction when heating to 1,100 degrees, which is our target temperature. Going back to 300 degrees Celsius, we see that the original dimensions are exactly recovered. So we are investigating now mixtures of calcium and manganese, perhaps with addition of iron, having abandoned the cobalt oxide, the difficult situation. And so now the material, of course, this is still at a relatively low technology readiness level. There is investigation going on at the material level, at the structured element level. In other words, there's a lot of extrusion, study of making extruded structures, foams of other ceramics, which will then be coated by the material, the thermochemical storage material, are also being investigated. So there's certainly some development to happen there, and hopefully we will have we will be at the stage at the end of the project of being able to look at at larger, let's say, demonstrations, or to go into pilot scale investigations. And so overall, what I would like to leave you with from this presentation is perhaps it's a bit early for us to discuss some forms of collaboration right now with what we have, but please keep us in mind in the future where we would like to have partners from this area as well, not only from the district heating end user, say, application, but also perhaps other applications which could be combined with the district heating mission, the goals. If we have something which it makes sense to look at a larger scale with some end users. Thank you very much. And I think we said questions at the end. Yes.